Hey everybody, we continue onward in chapter 22, which is the chemistry of benzene substituents. So it's kind of like, a little more detail into aromatic chemistry and sort of the reactions we can use in to attach benzene substituents and things like that onto benzene. So we're reviewing some benzene chemistry as we're going along. We're on topic 9 now, which is preparation of phenols and anilines. Remember, a phenol is an aromatic alcohol. An aniline is an aromatic amine via a reaction called nucleophilic aromatic substitution. Nucleophilic aromatic substitution. Sometimes we call this SNAR. Or SNAR. Okay? Alright. SNAR reaction. So let's think back a bit and recall that we never really learned a way to make a phenol. Have not learned how to do this, like taking a benzene and make a phenol, make an aromatic alcohol. We never learned it. There's no direct way to do it, so that's why you didn't learn it, right? And certainly not by EAS. No EAS method. Okay, and there's no EAS way to do this, but there are ways to make phenols. We can do it via SNAR. So we can do this reaction, substitution nucleophilic aromatic or nucleophilic aromatic substitution. We have a way to do that. So let's show an example of what a SNAR reaction is as a way to make a phenol. Okay. And there's a couple ways to make phenols, but this is one of them. Okay, so a simple example of a SNAR reaction. Simple example of a SNAR reaction is that if you have a leaving group on a benzene and you have a strong electron withdrawing group, EWG, maybe at the para position, ortho position, so this is para, but para or ortho or something. And you treat this with a nucleophile. Then you turn the leaving group into a nucleophile. So it's a nucleophilic substitution, right? Nucleophile attacks somehow and gives you kicks off the leaving group, Lg minus whatever. Okay, this is the general idea of a SNAR reaction. And the question is, how does it do this? And I mean, you might think, oh, well, I got a nucleophile attack the carbon, kick off the leaving group, right? Nucleophile attacks kick it off. Why does that not work? Why can't the nucleophile just go and attack that carbon? Well, the big reason is it's not, well, in an SN2 manner. Why can't this attack like an SN2 reaction? Attack, kick it off. Well, it's not sp3, right? It's sp2. So it will attack, but it's just not going to be an SN2 reaction. What do you think the mechanism is going to be? It's going to be called SNAR. Substitution nucleophilic aromatic. And what is the mechanism? The nucleophile attacks electrons move. So rather than just kick off the leaving group, the electrons move down and they keep going and going and going onto the electron withdrawing group. What does that give you as an intermediate? You get something like that, okay? And this actually has a name. It's called a Meisenheimer complex. I guess it was discovered by Jacob Meisenheimer. Jacob Meisenheimer. In 1902. So this was discovered pretty prehistorically in terms of chemistry goes. But anyway, so then the question is, how does this continue to react and give the product? How does the leaving group go away? Well, that's pretty easy now. Now the O- just swings all the way back. Kick all the way back and kick off the leaving group. And then that gives you the product. Okay, so that's what a SNAR reaction is. It's nucleophile attacks, push all the way onto a distal electron withdrawing group. And then the electron withdrawing group swings all the way back and kicks off the leaving group. In a way, it's not that far from like NAS. Remember NAS? You know, in NAS, you kind of do this something like that, where a nucleophile attacks, electrons move and kick back, kick off a leaving group, right? So like nuke. I'm trying to show nucleophile there, nuke, and that, right? So nucleophile attacks, electrons go up, electrons go down, kick off. Well, this is a little bit like that. It's just a little more of a distance for the electron movement to occur. Okay, so that's what the SNAR reaction is. I mentioned this in Organic 1. When I teach Organic 1, I mention this as a when we're learning about SN2. So remember learning about SN2 in Organic 1? It's a long time ago. And this is always around Halloween when I teach Organic 1 in the, this is usually on Halloween. When I teach about SN2 in Organic 1, it's on Halloween, and there's a funny pirate joke that goes along with it, which is, what's the pirate's favorite reaction, organic reaction? And the answer is the SNAR reaction. So pirates that always say "arr, arr, arr," they apparently like the SNAR reaction. So I found this on the web. It's what are the letters? It looks like it's phosphorus, iodine, radium, and tellurium to spell pirate. Okay. So anyway, that's what the SNAR reaction is. Okay. So what's the main requirement of a SNAR reaction? Main requirement. Well, there's kind of two, I guess. One is that you need a good leaving group. So it's usually maybe a halogen, bromine, chlorine. Interestingly, fluorine actually works for SNAR reactions. So sometimes we'll see fluorine as a leaving group for SNAR reactions. There's some reasoning for that. I'm not going to go into it right now though. But, and it also, strong electron withdrawing group in the ortho or para positions. Sometimes meta also works. Certainly in this, with this or this para substituted one, it was really easy to draw that for us. As para. Sometimes you can't cleanly show how the nucleophile attacks and how the electrons go, you know, deep onto the distal electron withdrawing group the way we did. Like if it's meta, you can't really necessarily draw that. But there are cases where, you know, with a meta substituted electron withdrawing group, we see the same exact effect. Okay. Okay, so a couple examples of the SNAR reaction. Now in this case, it's the benzene has kind of two electron withdrawing groups on the ortho and the para position. So you can say that the Meisenheimer complex is very resonance stabilized. We'll treat with ammonia as a example nucleophile. To make an amine, or actually an aniline in this case. Yep. And of course you're making HCl as a byproduct. Okay, so that's an example of converting a chloride to an aniline. Okay, what about this reaction? Would this work? Well, while the nitros are pulling electron density away from the benzene, methoxy is actually an electron donating group, so it's pushing electron density into the ring, and for that reason this doesn't work. Big X. So yeah, you need an electron withdrawing group. Nitros are good, maybe CF3 or sulfonic acids, maybe carbonyls, ketones, aldehydes, things like that. Those might work. Nitro is very common though for this. Okay. How about sodium hydroxide in this para-fluoro-nitrobenzene? Yeah, this works. And this makes a phenol. Para-nitrophenol. Okay, of course, without doing the full mechanism, it's something like attack, you know. You'd have to draw it out if you're showing the mechanism, the nitro. Yeah, but this is a way to make phenols, and then, you know, we just talked about, like, how do you make phenols? Well, this is one way to make phenols, is to actually substitute off a leaving group with a SNAR reaction. Okay. There's a cool sequence in the book. I'm not going to actually step through it. I'll just show the broad outline of it. We have a benzene, we have 4 fluorines. We have a ketone, alkene, amine, 2 carbons in an alcohol, and an ester. Okay, so there's a couple SNAR reactions going on here. SNARs times 2. 2 SNARs, where I think the nitrogen attacks and the oxygen attacks. So those kick off the fluorines. That makes this. Methyl ester. Single carbon. 2 fluorines left. Okay, and then they do another SNAR with this molecule. And here you got a secondary amine and a tertiary amine, which is the nucleophilic one, well, the one with the H on it, because it can form a 3rd bond. Well, it does a 3rd SNAR. And it probably kicks onto the ketone. I can't draw that. Part of the problem with drawing a benzene like a circle is I can't really do electron pushing that way. But if I wanted to show a mechanism, I would get rid of the circle and put double bonds, and then I could push all the way to the ketone, and then it kicks all the way back, kicks off a fluorine, and then you get this molecule, and I think they just do sodium hydroxide, saponification, so minus ester. It converts the ester into a carboxylic acid, right? Sodium hydroxide ester cleavage, so it makes the carboxylic acid. Well, anyway, so this is cool. This is they do a double SNAR, kick off these 2 fluorines to build this ring system. They do a 3rd SNAR, which attaches to this nitrogen, kicks that fluorine off to make this, and then you have the carboxylic acid. And this molecule is called afloxacin. Afloxacin, which is a quinolone antibiotic. Quinolone antibiotic. So, not useful for the coronavirus because it's an antibiotic, but it is one of the major clinical antibiotic drugs. And yeah, it's a pretty cool example of a synthesis to make this molecule. Okay. Oh yeah, one little other side note, just basic knowledge. I'm calling this a quinolone. A quinolone. So a quinolone is kind of referring to this sort of central top. It's a bicyclic. It's a heterocycle. It's called a quinolone. So maybe up here I'll show there's something called a quinolone. There's also something called a quinoline. I'm just going to mention those 2 things. Let's zoom out. I'll just show that up top here. Okay. So yeah, quinoline looks like that. A quinoline and a quinolone kind of has a ketone up top. So that's more of what a quinolone is. And maybe they'll, like, you can see the quinolone there. Okay, quinolone. And then I should also say, a lot of those anti-malarial drugs, and they've been considered for COVID-19 that turned out to be not very effective. They're based on quinolone. So like hydroxychloroquine chloroquine and chloroquine. Those are all quinoline-based antimalarial drugs. There's also something called mefloquine. Mefloquine is a really good one for drug-resistant malaria. Okay, anyway, that's it. Okay, so continuing forward, substitution of benzene with a weird intermediate called a benzyne intermediate. Substitution of a benzene through something called benzyne, and what do you think that might resemble? YNE, benzyne. Well, that's going to be a weird alkyne type structure, which is very weird when you think that we're talking about 6-member rings. And how could you have a 6-member ring with a alkyne in it? That seems kind of weird, right? Well, it is weird. And so this is the basic idea. We treat chlorobenzene with sodium hydroxide, NaOH. We actually make a phenol. And, well, I should say that that actually does not happen unless you cook this insanely hot to 340 degrees. So that's like very, very high temperature for most organic chemistry. So yes, this reaction kind of works. And you might think, oh, well, it's just going to be hydroxide attacks, kicks off the chlorine and makes a phenol. Well, that's not really what happens at all. It's a little different than that. So it's not via Eas, it's not via SNAR. Why is it not SNAR? Well, there's no leaving group, so there's nothing to accept to the charge like on the other side of the molecule. So it's not Eas, it's not SNAR. What else is it not? It's not SN2. Why is it not SN2? It's not going to be SN2 because you can't do a nucleophilic attack on an nucleophilic SN2 reaction on an sp2 center, right? This is an sp2 hybridized carbon. sp2. So if SN2 requires a tetrahedral hybridized carbon. Okay, so something's pretty weird. I'm going to summarize a whole bunch of interesting experiments with one little figure, because there's a lot that's discussed in the book, and we're gonna. I'll just mention that. If you say you do this reaction, NaOH, and we radiolabel this carbon as C13. C13. Okay, so it's got an isotopic label on the carbon containing the chlorine. It's a C13 labeled molecule. You would think, well, if we do this reaction, that you would get that, right? That would make sense, that if this is labeled with C13. Well, it turns out that yes, you do, but you also get about a 50% mixture with the neighboring carbon labeled. So that's weird. How could that possibly make sense if one carbon's labeled, you know, hydroxide, somehow changing the chlorine, and we're also 340 degrees, so we're still hot, very hot. Somehow the mechanism will kind of allow the hydroxide to either attach to one carbon, or it looks like maybe the neighboring carbon. One of those two carbons, or the, you know, and that, when we're talking about benzene, well, yeah, that's actually, that is what's proposed the mechanism. That experiment allowed people to figure this out, and also be able to model it using computers, and there's a lot of fun ways to investigate this mechanism. Okay, so what's the mechanism? The mechanism of this crazy reaction, this very high temperature reaction, the kind of accepted mechanism is this. So okay, and what did we call this? What was the name of the section? It was called benzene. So it's going to be some kind of weird alkyne type mechanism, and it is. It's not that crazy, but it's a little odd. Okay, so what happens? The first step is the hydroxide acts like a base in sort of like an E2 type reaction, where it takes the proton, kicks off the chlorine, to make this completely oddball intermediate called a benzene. Okay, there's evidence that it may actually first take off the proton and then make the triple bond. I just abbreviate it this way. So hydroxide takes the proton and then and then kind of just forms the other bonds. Although it may actually be two-step. Maybe two-step. If I ask about this on a quiz or something, this is totally fine. So yeah, benzene forms. Okay, and then now hydroxide, rather than be a base, we're going to have it be a nucleophile. Actually. So the first step, the hydroxide was a base. Now the second step, the hydroxide is going to be a nucleophile. And it kind of attacks and pushes a negative charge onto the neighboring carbon. Okay? And then the negative charge can grab a proton from water. That's how it works. Okay. Now, how does that explain the weird radio-labeled experiment? Well, if you think about how this might happen, hydroxide takes the proton, and then you get the alkyne, the benzene, and then the hydroxy can either attack, you know, once you got the benzene, the hydroxide could either attack one carbon or it could attack the other carbon. And either one of them would work, and that would give rise to two different radio-labeled products. Okay, so this is a pretty cool example of how radio labeling, you know, labeling specific carbons with like C13, actually aids in the figuring out the mechanism. Okay. I should also say that benzene makes anilines. So switch it up a bit and use bromobenzene. Use ammonia. Actually, no, let's not use that. Use a K plus NH2. Potassium amide. K plus NH2 minus. I think we need a little bit of water in there also, but it undergoes the same reaction, and it's the same kind of reaction. So base takes the proton, makes a benzyne. I'll just draw that. And then NH2 attacks it, and then you protonate or something, and it makes that. Okay, cool. I think this one's lower temperature too. I don't have the exact temperature. Lower temp. So it doesn't. This one does not necessarily need to be done at 300 degrees. Okay. I should also say, benzyne, not really synthetically useful. So we don't really use this as a method to make molecules because it's the high temperature, right? And if I have a crazy molecule with a bunch of functional groups, I don't want to apply high temperature to very many molecules because it'll destroy them. Okay, so but what is this interesting for? Why is benzyne even interesting at all? It's interesting for mechanistic reasons. Interesting mechanism. And you know, it's as organic chemists, we're interested in organic structure, and seeing this crazy weird intermediate is it's kind of cool, you know. It's extremely unstable and reactive, but yeah, that's benzyne for us. And lastly, yeah, there's definitely milder ways to incorporate interesting substituents onto benzene. And that's what we're going to get to next. Alright, so number 11 is one of these milder methods to incorporate things onto a benzene. Substitution of benzene via something called a diazonium salt. Diazonium salt. What is a diazonium salt? It's a weird nitrogen containing functional group. In a nutshell, it's RN. That's a diazonium salt, and there's an X minus. Okay, so it's some kind of weird R and triple bond N, and then plus charge on the middle nitrogen, and then X minus. Okay, that's what diazonium salt is. What are they, and how do we make them, and what can we do with them? Okay, so let's show a simple example. If we take an aniline, aromatic amine, and we're going to react this with nitrous acid, HNO2, and sulfuric acid, HNO2, H2SO4. This is actually, well, in the nitrous acid, HNO2, I guess since I've learned organic chemistry, we always abbreviate this HONO. Because nitrous acid is HO and double bond O, or HONO. And HONO is a reaction that will a reagent that will create a diazonium salt. And I'll show a nice mechanism for that in a second. Okay, but what you get is that, the diazonium salt. Okay, before I do the mechanism, what I'll show is, well, I'll point out that these are kind of reactive, so we don't like sit around and isolate them, but there are a gazillion of reactions you can do with them. So lots of conversions, and like I can convert a diazonium into like a bromide or a chloride or a alcohol or an aniline or a cyanide. There's all these different reactions, various reactions. Most of them are collectively called Sand-Meyer reactions. Sand-Meyer. Those will be a little later in the chapter. So we're not going to show all the Sand-Meyer reactions now. We'll see them though. Essentially though, this you could say is a very versatile intermediate. Versatile intermediate, synthetically useful. Very easy to make them. I mean, you just mix this with these two things, this gets formed, and then you have some other reagent that causes a Sand-Meyer reaction. Okay, so what is the mechanism of how it forms, how a diazonium forms? So let's draw out HONO. So there's nitrous acid. It's HON double bond O. And nitrogen attacks. You could protonate the oxygen initially if you like. I'm not going to do that. I'll just protonate it in the next step. Okay. So what does that give us? Benzene, NHH, and then we got an N and an O minus and an OH and a plus charge. Okay, maybe we'll proton transfer from the nitrogen to the oxygen. Remember, we had a positive charge here. Okay. All right, and I am going to kick off one of the OHs. This is probably assisted by the other acid that we have, present, sulfuric acid. So this could be protonated. For this simple mechanism, I'm going to skip that. Okay. What does that give us? Maybe I'll go down. Kicks off one. Then we can PT nitrogen to oxygen. Right? And then the other nitrogen just kicks that off. Left nitrogen forms a triple bond, kicks off the water, and you're done. And that gives us the diazonium. Okay? So yeah, they're pretty, the mechanism is pretty straightforward based on what you guys know, how you make a diazonium salt. Okay? Alright. So all these reactions, the Sandmeyer reactions, we're going to do later in the course, or later in this chapter, so today or tomorrow. But for now, let's just show one example of a cool thing you can do for now. Aqueous thermolysis. Aqueous thermolysis. What does that mean? Aqueous means water. Thermolysis means heating, just cooking. Delta sign, cook. Okay? And yeah, let's show this example. So if I take a aniline and I treat it with HONO, which is nitrous acid, that makes the diazonium. Okay, and treat that with water and a little bit of heat. That makes a phenol. Remember how just a while ago I said, you know, there's not really an easy way to put a phenol onto a benzene. Well, this is an exception. This is a great way to attach a phenol to a benzene. And what do you think the mechanism is for that reaction? What do you think the mechanism is for the diazonium being treated with water to make this? Well, do you think N2 plus might have a different ambition on what it might want to do? You know, it's got an N2 on there, or maybe it's really close to being what? It's really close to being N2 gas, right? So it really kind of wants to become N2 gas. And so what happens is it just pops off. It's a leaving group. This is a rare case because this is not a stable carbocation, but it is kind of probably what's happening. You know, it's not resonance stabilized. That's not a happy carbocation with the aromatic ring there. It's a double bond, right? It's a benzene. But anyway, once that happens now, water just attacks. And then loses proton. Okay? So that's kind of how an aromatic diazonium reacts with water to make a phenol. Okay? Mechanistically. Alright, and it's thermolysis with water. Here's a question. How do we make that? Is there a way to magically make that? Make an amine, aromatic amine? Well, not from like from benzene. How do we do it? There's no way to just turn benzene into this, right? We didn't learn that Eas reaction either. Just like we didn't learn an Eas reaction to make a phenol, we don't have a magic Eas reaction that makes a aniline, right? But we do know we can make them from nitrobenzene. Using a reduction, and the reduction is H2 palladium. H2 palladium turns a nitrobenzene into an amine. And then last question, how do you make nitrobenzene? Well, that's easy. That one we did learn in chapter 15 or something is HNO3H2SO4. We can do a nitration of a benzene with nitric acid, sulfuric acid to make the nitro group. Okay, and then from there we nitrate, we reduce to the amine, treat with HONO, makes the diazonium salt, and then treating with water and cooking it converts to a phenol. So this is actually a multi-step route to make phenols, and it works really well. Okay. Little synthesis question. What if we bromobenzene, and we want to make 4-bromo phenol. How do you do it? Well, now we know a way to sort of do this through this diazonium thing in HONO, right? So we could do this one going backwards pretty easily. So what's the immediate precursor of this? Step backward, let's do retrosynthesis. Retrosynthesis. Well, we make this from the diazonium. How do you do that? What's the reagent? H2O cook, right? So from a diazonium, you cook it with water, and that makes the phenol. Well, how do you make a diazonium? What's the precursor to a diazonium? The precursor to a diazonium contains nitrogen, but it's just the amine, right? NH2. And what's the reagent? HONO, or HNO2, and sulfuric acid. Okay, so HONO is the reagent, nitrous acid, that converts NH2 to diazonium. Well, how do we make a aromatic amine? There's no way to magically put it on from the benzene, but we can make it from the nitro, the H2 palladium. And then it's just a matter of, can we attach the nitro to the bromobenzene, and can we do it selectively? Because the bromine is, what kind of director is it? Remember what kind of director a bromo is? You have to review that all for your cumulative exam here coming up. But yeah, what is it? Is it orthopara director or meta director? Well, with the lone pairs on it make it an orthopara director, and so that's great because we want it to be para, and ortho is generally disfavored due to sterics. So that's cool. The only the question is, what's the reagent? And it's HNO3H2SO4. Nitric acid, HNO3H2SO4. The only other funny thing is that's HNO3H2SO4. HONO is HNO2H2SO4. So they're kind of easy to mistake, right? HNO3H2SO4, HNO2. If we just remember HONO, it's nitrous acid, it's the same thing. It's HO, N double bond O. Yeah, you get to the same point. All right, great. So that was a nice synthesis example. All right, so onward, and we'll come back to those diazoniums in a bit. Let's talk about a little bit back to phenols and the kind of reactions that phenols do. So first we're going to mention alcohol reactions of phenols. So considering a phenol is kind of an alcohol, like, does it act like a normal alcohol? Well, in some ways it does. Phenols are weakly basic. Just like a normal alcohol, it can be protonated. So, let's see. There's the phenol, and if you do like a acid base type reaction. And we'll assume water's a proton donor. You make this kind of derivative, and OH minus. And this is sort of showing, yeah, you can protonate a phenol, and it makes a highly acidic proton. So the pKa is negative 6.7. So this is a, not a very favored equilibrium because you're making something that's such a strong acid. So yes, you can protonate a phenol, but it's not a very favored equilibrium. All right, so we can either protonate a phenol, we can also deprotonate. Oh wait, let me see. Let's talk about phenol ethers real quick. Protonation, because we can protonate other things that are kind of like this. Protonation of aromatic ethers allows a cleavage mechanism. Remember phenol, sorry, I can't speak right now. Ethers, remember back to organic 1 ether chemistry, and so it's a carbon, oxygen, carbon. Those are very stable functional groups, but there's cases where we can cleave ethers and we can use strong acids to do so. So let's show an example of that. Okay, so this is kind of like what we were shown above with maybe a strong acid protonating a phenol, but it's not that favored. Let's just draw this as an example. Okay, so this is a aromatic ether, a methyl ether, and we've seen this a couple times throughout organic 1 and organic 2. If you react with nucleophilic acids like HBr or something like that, it cleaves the ether and gives us a phenol and like bromomethane. It's kind of like a Williamson ether synthesis going backwards, because remember, a Williamson ether synthesis is where you take an alcohol and react with an alkyl halide. Maybe first deprotonate it and then attack. So this is kind of like the opposite of a Williamson ether synthesis. Opposite of Williamson. Opposite of the Williamson ether synthesis. Okay? Alright, so what's the mechanism of this? This is easy. You just protonate the oxygen. Kick off a Br. And this is totally something that was learned in organic 1. It's pretty easy. You protonate, and then how do we kick it off and form bromomethane? Well, Br minus now. Attacks and kicks off OH. Okay, so that is that. It's the opposite of the Williamson ether synthesis. Okay, so that's kind of related to what we said about phenols being something you can protonate. But this is a ether cleavage with a nucleophilic acid. All right. We can also make ethers. Can make ethers. And how do we make them? We would use the Williamson ether synthesis. So now let's actually apply it backwards. Let's actually make an ether this way. Alright, so I'll just show you one silly little example to do this. Alright, so let's take benzaldehyde. And we'll nitrate it. HNO3H2SO4. Well, actually, what I'm going to do, I'm going to turn this into a synthesis problem. So let me do that on the next page. Okay, so let's just, we'll do a Williamson ether synthesis type based mechanism problem on the next page. Okay, so let's see it. Let's think about this. I'm gonna synthesis, and we're gonna start with this aldehyde, and we'll go all the way long synthesis to that's carboxylic acid. Make it aldehyde. Okay, and we will have maybe as our final product that. Oops. Okay, there we go. So we're attaching a propyl ether, right? There's no easy way to do this. This is going to be a multi-step synthesis, okay? But we do know that we can make ethers. There's my little squiggly line. I can make an ether from a phenol or an alcohol. So the last step might be take that alcohol and attach a 3-carbon piece. So back from organic 1, how do you do a Williamson? It's, well, you have to take off the proton, make a good nucleophile. So step 1's a base, and then step 1's a base, step 2 is the electrophile. So maybe NaH or even NaOH, almost any base will take off this kind of acidic proton. And then how many carbon piece? It's 3, right? 3 carbon piece. So maybe bromopropane. Okay, so that was doable. Now it's a question of like, how do we go from there to there? Well, this is going to be, we just sort of did this sort of synthesis a second ago. This is a meta director, right? Meta. So this goes quite well. I'll expedite this a bit. How do we go from the amine to the phenol? Assuming we have the amine and we want to go to the phenol, first it's 4-letter hono. That makes the diazonium, and then it's water cook, and that converts the diazonium into the phenol. Now, how do we do this? It's 2 steps also. Step 1, step 2. First step, nitration. Meta nitration, because that's a meta director. HNO3, H2SO4, and then we make a nitro. And how do we reduce the nitro? H2 palladium. Yeah, okay, so that was a nice multi-step synthesis to make this sort of meta substituted ether derivative, right? Other chemistry, phenols. Can we convert a phenol to an ester? And the answer is answer is yes, and it's very easy. So let's just show how, if I have a random phenol, and we have a methyl ether on the left, phenol on the right. Anyways, we can I don't know, make some kind of ester, right? How do we turn a phenol into an ester? Well, maybe we could use the carboxylic acid. Right, and that's what would be the reagent if we're doing that? Phenol plus carboxylic acid. That looks like it's another name reaction. What is it? It's a Fischer Esterification. Fischer. How do you do it? You protonate. You need an acid catalysis. So the C double bond O attacks the proton, makes an RSCC. Phenol attacks, etc. So it's just like making an ester through normal Fischer Esterification. Any other ways you could do it? We could do acid chloride. Right, that's the other way we've emphasized making esters. So the phenol would attack the carbon, and then the base would take the proton, and then electrons kick off the chlorine, and you get the product. Okay, so we call that using the nomenclature we used before. It's base mediated NAS. Base mediated NAS. Okay, all right, cool. Continuing forward, let's think about Eas reactions. What's an Eas reaction? It's a electrophilic aromatic substitution. So this is all chapter 15, 16, right? And Eas reaction of phenols. So given if you have a phenol, what kind of reactions can you do? Eas reactions of phenols. And we did talk about this before. It was the idea of reactivity modulation. Remember that? How if you have a phenol, it's kind of extra activated, intermediate, and we need to decrease its activity. This is all chapter 16 stuff. Okay, example. That if you take a phenol, for example, and we nitrate it, well, this is actually a very easy reaction, because this is a, what kind of director? Well, it's got the lone pairs on it, it's an orthopara director, and nitro gets attached probably at the para position. So this is a very simple example, NO2, and yeah, Eas, chapter 15, or 16, I think. I think 16 is where we talked about orthopara directors and all that kind of stuff. Maybe chapter 16. Okay, so yeah, and then this is actually kind of cool because this, while the hydroxy group is a strong activator, the nitro is a strong deactivator. So this is an activator, and this is a deactivator. Yeah, and and so, because sometimes the problem with phenols is that they'll react once, then they'll react multiple times. The nitro is such a good deactivator that it pretty much stops. What we learned in chapter 16 was that sometimes it's different, and we gave the example of a phenol reacting with Br2 and FeBr3, and what happens is it brominates just like you would expect. It's an orthopara director, right? And it attaches to the para position, but it only keeps going and going, so it doesn't stop. And you get this exhaustively brominated product. And okay, and what we talked about in chapter 16 was like, well, we can modulate the reactivity. We can do something to the phenol so that it stops. And that was all learned previously. We'll review it as a mechanism to prevent that from happening. One other interesting thing about phenols, because we learned that to do this Eas reaction, this is, you know, it's an Eas. We learned when we did Eas reactions that you need Br2 and FeBr3, right? Well, interestingly, this phenol is so reactive that you don't even need the FeBr3 because it's so reactive. It's like the FeBr3 made Br2 a super electrophile, right? We did a mechanism for that. I'm not going to show that again, but Br2 interacts with the iron and it makes it a super electrophile. Well, this is so reactive that you don't even need to do that. So you can do this with Br2 even, okay? So that's just a little note. So what's the solution to this reactivity problem, and say like we want to actually form a mono-bromo product, a solution, modulate the reactivity, right, of phenol. That would be a solution. And so example, there's kind of two ways to do it. One is simply do a Williamson, NaH, like methyl iodide. So Williamson, base takes proton, NaH, takes off the proton, makes O minus, kicks off the methyl, the iodide, and you make a methyl ether. Somehow, and we talked about this all in early days of this semester, chapter 16, this is a little bit less of an activator than this. And so when we do bromination, and I think now you need the iron. Now you get a clean mono product, okay? So the methoxy is a little bit less of an activator, and then you get this. So we've modulated the reactivity of the phenol by making a methyl ether. And then how do you take off a methyl ether? Just learned that. We reviewed it just 5 minutes ago. How do we do it? Just use a strong acid, strong nucleophilic acid. HBr, you can use HI, hydroiodic acid, yeah? One more way to do this. One alternate way. One more. And it's the same idea, we're just going to use a different modulating group. So we can use acetate. So use an acid chloride and pyridine, and that just makes an ester, right? You did learn this in chapter 16. It's crazy. Okay, so we just made an ester, right? And just like the methoxy, this is also a slightly worse activator. So now we do Br2, FeBr3. It brominates para, because that's still an orthopara director. How do we know it's an orthopara director? You know, why are these all orthopara directors? Hydroxy or methoxy or this? It's because they all have lone pairs, right? Right, the lone pairs indicate directing ability. Okay. All right, so yeah, I drew this. I didn't draw this perfect. It should be a little more connected to the oxygen, but I'm not going to fix that. All right, and then we make an ester with the acid chloride, the pyridine. That makes this. Then we remember when you learned this in chapter 16, we didn't even know the NAS reaction yet. So we just said, oh, it's magic, right? This is all magic. Well, now it's not magic. You actually know how this works. It attacks, pyridine takes the proton, and does the NAS mechanism. NAS. It's an NAS reaction, okay? Well, anyway, then we do an NAS, then we do an EAS, electrophilic aromatic substitution, and then if we want to make this same product, now it's not HI, because HI is the ether cleavage reagent. If we want to cleave an ester, we would use sodium hydroxide. Right, it would be a base-mediated saponification. Hydroxide attacks the ester, kicks off the oxygen. Okay, cool. So yeah, that was kind of the idea of reactivity modulation that we learned in chapter 16, applied to phenols. Alright, so let's, we have two quick reactions now. Kolbe-Schmidt reaction. This makes salicylic acid, which is the precursor to aspirin. It's actually, and it's a pretty easy reaction, so it's not that crazy. This is an Eas reaction, a common Eas reaction of phenols. So let's just show it real quick. It's not that traumatic. Okay. It's a kind of a funny Eas reaction. All it does is it takes a phenol and it adds a carboxylic acid next door. So mechanistically it's K2CO3, which is a base, and then CO2, maybe water. Okay, how does it work? It's really not that bad. So the base, which is K2CO3, you could draw that out as K plus, and then CO2 minus. I'm just going to call it B dot dot here. Base takes the proton, not that bad, right? The only recommendation I have is to draw your benzene this way, oriented this way, with the double bond on the right. Okay, and now we have O. I'm going to draw the K up there covalent. It could be ionic, it could be covalent. It's probably more ionic, but for this mechanism I draw it covalent, kind of poking out up there. And the other thing I'm going to do is a little weird, and I usually don't do this, but I'm going to draw a CO2 bent. Okay? That looks a little weird, right? Well, for the mechanism it's going to help. So now we just do dot 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 and then dot 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 dot. So we can kind of see sort of like a 6-member ring. 1, 2, 3, 4, 5, 6. It's like a 6-member ring type thing. Okay? And the mechanism is actually kind of concerted. And the potassium is sort of interacting with the oxygen. It's delta positive, delta minus, right? So that explains kind of why this happens and the CO2 attaches to the ortho position. Well, nevertheless, the mechanism is really easy. This just swings down, this goes there, and this goes there. Right? It's a sort of concerted looking Eas reaction. And there you go. That makes the potassium salt of the carboxylic acid. That's all the hard work, and now it's just simply a base, water or something, re-aromatizes. Okay, and then some kind of pregnation, I don't know. H3O pregnates the oxygens and gives you the product. So it's not that bad. The weirdness is maybe the first step, how it kind of sets up for the reaction. I like to get it ready for this six-member ring intermediate. Okay? Alright, so then we have one more that's almost the same looking thing. And then we're done. 5. This one is called the Claisen Rearrangement. Claisen Rearrangement. It'll be kind of related. It's not that bad. So it's good to just have these kind of grouped together because they're sort of related. And this one is a electrocyclic reaction of benzene. They both happen to phenols. So I'll focus on the Claisen, then I'll show them both side by side. Alright, and then we're done. So now I'm going to draw benzene phenol. For this, I'm going to do 3 steps. Actually, I'll do the 3rd step separately. Okay, so what does this do? This is the Williamson, right? Base takes proton and then it attacks. So this gives us a ether, right? Williamson ether synthesis. That is not that crazy. That's actually very easy. The the NaH is H dot dot minus, right? It's a basic H dot dot minus. As opposed to, when is H dot dot minus nucleophilic? Because this is H dot dot minus that's basic. The nucleophilic H minus is usually like NaBH4, lithium aluminum hydride, diol, NaCnBH3. Remember all those? Those are all the nucleophilic hydrides that we're used to. NaH is more used as a basic hydride. It's used for Williamson ether syntheses and stuff. Well, anyway, so this is easy, right? Nothing weird yet. And then we just do SN2. Okay, how does that work? It's just O minus kicks this off. Circle lone pair, O minus attacks carbon, kicks off the Br, and cool. So now the weird thing happens. So, and then we're done. Not even that weird, but a little weird. On heating something happens where this group, what's the name of this group? It's called an allyl. A-L-L-Y-L. The allyl group transfers from the oxygen to the ortho position on the benzene. Okay, so yeah, let's just show it. It's not that weird. The trick is to line up the allyl let me redraw. We need to keep the benzene the same. Let's make sure the double bonds are all the same. That's going to help us. Okay, double bond, double bond, double bond, right? And all I'm going to do is down, down, down like that. Wrap it around, wrap it down to the near the other double bond. Okay, that's the key to getting this mechanism to work. Dot, 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 dot. So set up a dot, dot, dot from the ortho position. And now it's just going to be a very simple thing where this goes there, this goes there, this goes there. That's the hard work. Now you get a ketone temporarily. And all you got to do is 2 steps. It's really, actually, you could say PT actually, PT. It's really, you're enolizing, right? You're tautomerizing. So this goes there, you form a double bond, make an O minus, and then the O minus gets protonated. It's technically a PT, and it's okay for you to say PT. If you're doing this mechanism, just say proton transfer. Or if you want to draw the intermediates, maybe do it in your notes. Have the base take the proton, make a double bond O minus, and then the O minus grabs a proton. All right. So we are done. I'll just zoom this out, and we'll just look at them both. Look at all the mechanisms side by side. Schmidt, you're attaching a carboxylic acid at the ortho position. by base taking proton, and then just kind of line up CO2 in a weird manner. For the mechanism, just draw it kind of like angled like this. The only thing I could have done better is try to maybe make this a little more like a hexagon. It's like, make it a little more hexagon-like in your notes. That's ideal. I didn't do it too well here. Yeah, make it like a hexagon. Yeah. Okay, and yeah, then it's just a 3-arrow concerted mechanism. Get a ketone, grab the proton, O-, and then some kind of protonation step. Salicylic acid, yeah. And the Claisen rearrangement is simply a Williamson ether synthesis with allyl bromide to make this allyl fragment, and then we just cook it at, I don't know, 100 degrees, 200 degrees, and then the allyl group kind of just transfers to the ortho position. That's called the Claisen. And then, of course, lastly, why do we care about salicylic acid? It's because we use it to make aspirin, right? So acetic anhydride, it's a little messy, I'm sorry. You know, what's the relevance of this molecule? It's used to make aspirin, right? Aspirin. Okay, yeah, it's just an Eas reaction, hydroxy attacks, kicks us off. And this is like the commercial synthesis of aspirin, how aspirin's produced on multi-ton scale throughout the world. All right, well done. Sorry, I went a little bit over. But yeah, those are the two cool reactions, Colby Schmidt and the Claisen.